quickly now. What is this part here? Yeah, so let me show you my screen. Do you see my screen, guys?
Yes.
Yes, okay, perfect. So what this is eViews, guys. If you open eViews, eViews is a very simple package that allows you to do, you know, if you want something quick, eViews is one of the packages I use a lot. I used to use. Now, if you really want to go serious, you need to use MATLAB, R, Python, something like that. But this one here allows us to basically start working and understanding what we are doing. Okay. The first thing we are going to do, guys, is we are going to use this data set that we call a very simple one. We call it, how do we call it? The name of the file is, yeah, simple linear regression data. You have it. Okay, it's a very simple Excel file. Do you have it?
I'm sorry, Professor. I'm still not very familiar with eViews. Where should we be looking for this?
No. This is Excel.
Oh, okay.
I send you this file. This is
yes,
Excel,
I have that.
And yes, just open the file. Just understand. Let's understand what we have here in Excel file. Okay, so we have two variables, guys. I told you this is the grade on admission exam, and this one here is the productivity rate. Got it? And then you can see the graph here. So let's learn how to import the data into eViews, and then we can do some small regressions and understand everything. Okay, in 5 minutes we're going to be up and ready. So if let's go here. So now I'm in eViews. Everyone is with me? Yep. Oh, sorry, why I'm not appearing. Yeah, are you with me, guys?
Yes.
Okay, perfect. So let's go, and then we go File. When we want to start a new file, guys, what we do is File, New. So we go File, New, and Work File. Okay, so this is the first thing you need to do in eViews is to create your work file. So we're going to import data, create equations here, analysis, etc. So we create a work file. And then when it asks you for data, you can enter annual data, monthly data, quarterly data. But in our case, let's do this one here, unstructured and dated. Okay, and what you need to realize is how many observations do we have? We have just the number of observations, we have 5 observations, okay? So number of rows. Okay, so what we say here is number of rows is simply 5. And with that, we are done. So this is your work file. And it's empty. This C corresponds to the coefficients. And the receipt is simply the residuals. Okay, at this point it's empty. There's nothing. It's simply a work file. It will have 5 observations as we have defined and dated as we have defined. And once you are here, guys, what you do is you simply go, now we need to import the data, File, Import, Import from File, and then you look for your data. So I think I have it somewhere here. Then you look for where do you have the data? Where do we have this data? So, yes. Here. Do you see that? So you simply go File, Import, Import from File, and then you look for where do you have your data? Then you simply put Open, and it detects for you. Do you see that? Okay, the title, the data. And that's it. If you want to do a custom range, so if you want to select only a piece of your data set, you can do that clicking here. You can also, if you have multiple sheets, you can also select the sheets here. You see, CAPM data, we can use the CAPM later. And then you simply click next. Yeah, the dates are 1, 2, 3, 4, 5, 10. Okay, I have the headers. And that's it. And finish. The names, guys, normally don't use this type of underscore names or empty names with empty spaces, okay? So it's much better, much cleaner if you have the names very, very small. Okay, from here, what we can do is we just click here. Is everyone with me?
Professor, I have a quick question. When it asks you to link imported series and alpha objects to external sources, I'm supposed to click no, right?
Yes, no, because yeah, I click yes. Hopefully not. Yes, because what you need to create your data set in this work file. It's much better. Okay. Otherwise, what it will be doing is will be calling the data from outside sources. And sometimes if you change the address of the data, then you're done. I will redo this again. Okay. Yeah, that's a good point. So we'll delete. I will do the same. File. Import from file. Again, and go process. Anyone? Okay, so this is okay, this is okay, this is okay. I finish. Link for here we go. You see the color is different. When the color is different, guys, this means that now that when you save this file here, the file is going to save with all the data. All right. Normally, when you want to link with external sources, is when you have these huge data sets that you don't want to have in the program. You simply want to call them, use them, and just leave it there. So that's why you use these type of things. Is everyone with me?
Sorry, Professor.
Yep.
You sent us a work file today, and you sent us another.
Oh, no. The Excel file I sent you perhaps 2 weeks ago. Okay. We're not just using that file. Okay. I sent you this file together with the CAPM date, etc. Okay. I think it was 2 weeks ago.
Professor, could you just repeat what you did when you first opened eViews? You did file, new, and then...
Oh yeah, file, new, work file. This is the first part. And so it creates an empty work file. And then what you do is, I can do this again. So just if you don't have the structured data, so means weekly data, monthly data, daily data, simply do unstructured. And then what you need to do is count the number of rows in your data set, in this case 5. And then you create your work file.
Thank you.
Okay, perfect. And once you have that, now you import the data. So it's file, import from file, you look for your data, etc. Right? Is everyone with me here, guys? I will take a couple of minutes just to be sure that everyone is with me.
Professor, I'm not really sure why, but my eView seems like it's a bit different from yours in that the capture is at the top left of the screen and command is like a separate tab that just says command.
Oh, don't worry. I think yours is I don't know if it's a student version. I'm not sure, but don't worry about that.
Okay, just want to make sure. Thank you.
Yeah, yep. Don't stress with that.
Professor, we're on eView 11. That's probably why it's happening. You're on eView.
Yeah, 12. I mean eView 12, I think, right? Yeah, eView 12. But that's okay, guys. No stress with that. Okay, is everyone with me? Yep. Guys, Okay, so now what we can do is the first part is looks like Excel. So let's create, for example, let's take a look to the data. You double click and then you can see the data. Make sense? So if you want to see, or let's open this one. If you want to see a graphical representation of that, you go view, graph. And of course you have many series here, many options here. You simply click OK. And so this is the data. And then you can play here, guys, is very, you can see, you can do whatever you want. Now, the other thing that is important is when you want to see two things at the same time, you just shift and click as many, control or shift. So you do this one and control here. So I want to select X and Y. Once you have that, right click, open as a group. Okay, so I've selected X and Y, then right click, open as a group, click there, and then you have both variables here. Got it? So now what we can do is, for example, graph. We can do a scatter diagram, perhaps. And this is what we have. Okay, so you have a bunch of other things that you can add here, guys. We can add, for example, a fit line if you want. Are you with me? So when you click here, right click in the graph, right click options, and then you can add a fit line, more or less like Excel. Remember, let's do a regression line. Just click OK, and then you have your OLS line. Now, yes.
Sorry to interrupt. So where was the graph option? Can you?
Oh yeah. First of all, you need to create a group. Have you?
Right.
Are you in a
yeah.
group?
I have the group.
Yes. Okay. So once you have the group, you go view, graph.
Oh, got it.
Okay, and then I've selected the scatter diagram. And if you don't want to have anything here, none. Simply just to see the points, none. And then you can add the line. You can start playing with this. Okay. Make sense? Now, guys, if you want to change the order of the data, so for example, you want a productivity rate to be the X and the dexterity score to be in the XY, what you do is you go view, group members. And what you do here is you simply move these two on top. You see that? You just click on them and then just move it up as you want. Got it? So if we want to see this one here, if we see the graph now, this is another scatter. Oh, sorry, I didn't move the group members in. So you should be down. Yeah, okay, so now let's go and see. Yes, you see that? Now my Y is in my X-axis.
Professor, just a quick question. How did you isolate the X and Y into a separate window where you can drag it down and drag X to under Y?
Oh, here, you go group members. This is what you mean. You go in view. Okay, so you have the two, okay, listen. You have these two. And if you want to change the order of these ones here, you go view, group members. And once you have that, you simply select the one that you want to move. You simply move it. Got it?
And then I'm going to have to redraw the graph, right?
Yeah, and then we draw the graph. And then we do graph, scatter diagram, here.
Got it. Thank you.
Perfect. Okay, so we have a grouping, we have graphs. So now let's take a look to this view, guys. This view has a lot of things here. Now, for example, we can do descriptive statistics. Okay, we can do individual samples. Okay, view descriptive set individual sample. So this is the mean. So we have the mean, the median, the maximum, the minimum, etc., etc., etc. Like Excel. Okay, guys, make sense? Perfect. If you want to save a group, you need to name it. Okay, I will call it group 1. You can change the name here. You can write a description here just to remember what you have. Otherwise, if you don't save the group, guys, eViews normally, if you create another group, it's going to delete the previous one. Got it?
Professor, very quickly, how did you save a group again? Sorry, you had a...
Yeah, view, no, view, sorry, name, and then you simply name it.
Got it, thank you.
And this will appear immediately in your work file. Okay, then I can close this group. So we have descriptive statistics, graphs, etc. So now we can go to do a very simple OLS model. Okay. So my OLS model, in order to run my OLS model, guys, I do quick. Okay, we're going to be using all the time this one. So outside, you have on the top a quick button here. Then you go estimate equation. And by default, guys, we have the OLS model. Okay, now, if you click here, we have tons of things, guys. Non-linear OLS, ARMA models, you know, the GMA model. We have tons of things that we hope we're going to be using some of them. Got it? But for now, my OLS, and the regression happens, you need to write the regression as you have as you write in a normal regression. So what I will do is my productivity rate, I will type, productivity prot rate, this one here, tab, space, C, this is small, C is constant, okay, space, the other one is this one here. So this is my regression. So this is Y. The name is kind of weird. This is my Y. C stands for constant. And this one here stands for X. Guys, questions? No? So, okay, so we run. And this is what we have. The same as Excel, guys. So we have the coefficients, 19.2, 3, the standard errors, the t statistics, and the probabilities. The probabilities are the p-values. Then we have the R square, the adjusted R square, the standard error of the regression. Then you have the sum of squares of residuals, etc. You have the F. Do you remember this one here is the ANOVA test? This is the F, and this is the p-value of the F test. We're going to be analyzing all this part here later. We don't need this. So now, guys, as a review, very quickly, who can read the R square? What do you read by the R square?
How many % of the variability in Y is explained by the variability of X? Perfect,
excellent. That's it. It's variability of X explained the variability of Y. Okay, 91%.
So R square is like an error, right?
Sorry, like what?
Like an error value?
Like an error value? No, well, it considers the sum of the squares of the errors, but it is not an error value. It's a ratio, basically. It's a ratio of how well the variability of X explains the variability of Y. Remember the formula is sum of squares of the regression divided by sum of squares of the total, or 1 minus sum of squares of the errors divided by sum of squares of the total. Yeah, so this is a ratio. We did the math last class, guys. Now, guys, why this R square is different from this adjusted R square? And which one do you prefer in this case?
The adjusted R square.
And why is that?
Because it's a small sample.
Exactly. Okay, the adjusted R-square, guys, what it does, it controls better for small samples. Okay, so normally when you have a small sample, you prefer to use the adjusted R-square. Perfect. What is the null hypothesis of the F test or the ANOVA test or the goodness of fit test, also known?
That there's no linear relationship.
Exactly. And so what can you tell me about this hypothesis? This is the p-value of the F test. Alpha significance level 5%.
Well, it's greater than alpha, therefore you don't reject the null hypothesis, right?
Wait, no. It's smaller than alpha.
Oh,
Because remember,
0.01. Sorry,
yes.
I need glasses.
That's right. So it's smaller. So this implies that we reject the null hypothesis, correct?
Yes.
But in this case, rejecting the null hypothesis is good because we are simply negating the thing or rejecting the thing that there is no linear relationship. So this is good. Okay. Now, if we go to the individual coefficients, guys, what can you tell me about the constant is not significant at the 5%?
Wait, Professor, you mean to say near its linear relationship, right? Because we rejected a null hypothesis of there is no linear relationship, which means near its linear relationship.
Yes, that's right. So the OLS model, remember, that has a linearity assumption on board. Yeah, it's okay. Okay, so now, guys, what can you tell me about I believe that I think that this number here, the constant, is not significant. So first of all, what is the meaning? How do you write in statistical terms, in mathematical terms? What I'm saying when I say not significant.
It is statistically equal to 0.
Exactly. It is statistically equal to 0. Of course, you can use the T statistic, but the easy thing to use is the prop is the p-value. So what can you tell me at 5% significance level? Reject or not reject?
Do not reject.
Do not reject the null hypothesis, guys. So technically at the 5% significance level, this number here can be considered statistically not significant, even though the number is 19.2, larger than this 3, but statistically this number could be considered 0. Got it? Now, what about this one here? We are going to use a test in a couple of minutes. So what about this 3 here? It is statistically significant or not?
It is.
It is. Why?
Because the p-value is less than alpha.
Exactly, and that's it. Makes sense to you guys? Now, what is interesting, guys, so this is up to now is accept, okay? Now, I will show you a couple of things that are really interesting here and we're going to be using all the time. So sometimes, guys, we have hypotheses, okay? So, for example, historically, this score should be equal to 1, for example. I don't know why, I'm just inventing a number. Or this number here should be equal to 0 or equal to 1, okay? So how do we do that test? You go coefficient diagnosis. It's coefficient diagnosis, sorry. Oh, before that, you have, when you go in view again, when you are in this, you go view, you go actual fitting and residuals, and let's do the graph. And this graph is very useful because it tells you, for example, my actual is the kind of a orange one, my fitted is my green, and my residual is my blue one. Yeah, you can see, the fit is very decent. Agree with me? Okay, so for that I did view, actual fitted residual, and then I did a graph. Now go to coefficient diagnosis. Now what we try to do is we try to change the hypothesis that we use 0. Okay, so 0 implies significantly different from 0, but I can have another idea to test. So you go coefficient diagnosis, Wald test. Okay, and so let's test here. So now what you need to understand is that if you consider C1, C2, C3 in the order they appear in your regression. So C1 is what? Is a constant. C2 is what? Is the X variable. And what I want from here, I want to test if this one here is equal to 0. Got it? Then you click OK. And here we have a bunch of statistics, guys. I need to show you where I show you my screen here. Let me share. Let me draw here. Now, we have basically, guys, two types of tests. Okay? So we have one that is called the maximum likelihood test. And the distribution of a maximum likelihood test, guys, is a chi-square, okay, with m degrees of freedom. So this is the chi-square. M degrees of freedom, normally this M is number of restrictions. Okay, so these are generic tests. One is called the maximum test, the maximum likelihood test, or the LM test, also they call it, Lagrange multiplier test. That's correct. LM test. So the LM tests are always in this shape. It's always chi-square. And then we have the other type of test, Wald type tests. And this is going to be distributed as M, N minus K, M. Yeah, let me see if I adjust this one here. Yeah, we can adjust this element. Okay, so N is what? Number of observations. K is number of coefficients. And M, as before, number of restrictions. Oh, sorry. No, where's my?
Excuse me, Professor.
Yes, sorry, there is it's the opposite, should be the opposite. Give me 1 second. Yeah, yes, because M is my control variable. Okay, so this one here is going to be M, N minus K. Okay. Number of coefficients, upset. So this one here is number of observations. And let me delete this one here. This is number of restrictions. Okay, what is interesting, guys, is the following. When you have a large, a small sample size, small sample, small number of observations, you prefer the F test. Okay, so this one here is better when you have small samples. When you have large samples, what happens is that chi-square M degrees of freedom will tend to the M, to the F and N minus K. So they approximate to each other. So when you have large samples, you are indifferent to use either.
Professor, what qualifies as small sample and large sample?
Yeah,
Is it
you know,
follow
that's a huge discussion. So you normally, the people are always arguing about 30 number. There is a, I don't know why, but I always say, let's say 100 and above should be kind of a large sample. Okay. When we have done simulations, guys, sometimes we got between 250, 300. No. Now, in financial econometrics, guys, we don't worry about that because the sample sizes are so big that we don't care. But in macro applications, micro applications, yeah, you need to be careful about that. And if you see the significant difference between the chi-square and the f, always select the f. You know, if you have, because the difference is going to be if and only if the sample size is not large enough. If the sample size is large, you're going to see that both values are going to be close by. So the decision rule is going to be almost exactly the same. Okay, so now let's go to reviews, and this is what we get here. So the t-statistic, forget about the t-statistic. This one here, the f statistic, you see, m is 1. I have one restriction. The coefficient 1 equals 0. 3 is n minus k. K in this case is two variables, alpha. I have the intercept at my x, so I have 2. So I have 5 observations minus 2, 3. And this is the value, 0.0874. And if you use the chi-square just needs the restrictions. I have one restriction. And according to the chi-square, here you can see this clearly. The chi-square is 0.01 versus 0.08. Okay, so here's when you need to decide which one I should use, f or chi-square.
Professor, we're still looking at your whiteboard.
Oh, don't tell me that, seriously. Okay, so let me go back. Now
we're good.
Yeah, good. So let me repeat this part here. So what we have done is we have done coefficient diagnosis, we have done Wald test, and in Wald test, what we have done is I believe that my intercept equals 0. So this is my restriction. So I have only one restriction. All right, so m equals 1. If you see the equation here, guys, oh, well, I don't have the equation here, but my equation is a simple regression, constant, and x, right? So k is 2. Remember the f statistic is m, n minus k. So m is 1 restriction, n is 5, k is 2, 3. So this is an F13, and the p-value equals 0.0874. And when you use the chi-square, guys, you have m only. That's the only parameter that you need. So the chi-square, 1 degree of freedom equals 0.01. Got it? So, and you can see here, if alpha is, if the significance level is 0.05, 5%, which one do you select? According to this one here, you don't reject the null hypothesis. And according to this one here, you reject the null hypothesis, correct? So we have a contradiction here. Which one do we select?
The F.
The F, why?
Because it's a relatively small sample size.
Exactly, it's very small, 5 observations is very small. Do you see that? So that's what you need to understand what we're doing, guys. Questions? It's clear? Okay, so if you want to save, if you want to go back to the estimate, to the model, just click estimate. Appears again, and then you simply click OK.
Professor, if I could ask a quick question.
Yeah, go ahead, John.
Does that small sample size not also apply to the chi-squared value as well? Or are those two different, like?
No, the chi-square is independent of sample size.
Okay.
Remember, the chi-square only has m. M is the number of restrictions, so it doesn't consider m. You see?
Okay.
The F is the one that considers the n. So that's why the F is more robust to small samples. Okay.
Thank you.
Perfect. Now, if you want to save these results here, guys, what you need to do is you estimate. Sorry, no estimate. Name, and then you can name it as you want. If I want to keep this in my file, I simply call it whatever, X and Y, equation, or whatever, and you can write a description. And you just save it as equation 1. Got it? Okay, now how do we save the file? The work file, you simply go File, Save As usual, and you save it wherever you want. So let me look for a place for this one. Yeah, I will say, I can call it example one. The extension is going to be WF1. And then I have this up already. Okay, questions?
Quick question. Yeah, when I'm trying to save a work file, it's asking me to save it as a single precision or double precision.
Double precision. It's much better double precision. You know, it goes, I think, I don't know how many decimals, 8 or 9, I don't remember. Yeah, but it's much better double precision.
Got it. Thank you.
Sure. Okay, done. Questions? Now, for next week, guys, as a matter of practice for you, remember that Excel file has two things. This Excel file has a different tab that is called CAPM. This is the CAPM data that we had. So what you can do in order to import this data, simply import the data, compute the returns, and run the CAPM model that we did in Excel, okay, using eViews. Got it? So this is your first kind of practice assignment for eViews. When you want to compute formulas in eViews, guys, you use this part here. Okay.
Professor, is there a way to just copy over the data from Excel and then just paste it over on Microsoft?
Yeah, you open the Excel here and then you simply drag it into here. Yes, you can do that.
Thank you.
Okay, guys, questions? Easy. So now what I will do is I will close this one here. And can you please open the one that I sent you today? I sent you a data set. So let me explain the data set first. Where's my data set? I think it was here. APT data. Yeah. Oh, yeah, I don't want this. Yeah, that's the issue that once you have this one, sometimes Excel. Yeah, so this is my data, guys. Okay, I have quarterly data, okay, from 2002 up to I don't know when. Okay, I have then 162 observations. I will do undated, so just to run. I have 162 observations. That's something I need to know. And what I have is the GDP. I have the 3-month CDs. Okay. I have IBM quarterly and SP500 quarterly. Got it? Now, what is interesting, guys, is that even though this one here is 3-month CDS, this 5.67 represent an annual rate. So this implies 6.67 per year. Okay, so just remember that. GDP is quarterly GDP, IBM is IBM, and SP500 is SP500 per quarter. However, the 3-month CD is represented in a yearly basis. Okay, even though it's called 3 months, this is not a 3-month number. It is a 12-month number. Okay, so just keep this in mind. So if you do all the process of importing, creating your work file, etc., etc., etc. So what you are going to end up is with something like that. So you don't have this. You are going to have CD. So this is the data, 567, 572. You are going to have IBM, 7841, and then you're going to have SP. And that's it, right? So you have 3 variables. I have the CDs, I have IBM, and I have, what is this one here? Oh, the GDP. Let me see if I have these ones here, correct? Are you seeing eViews also, right? guys? Oh, I have something missing, IBM. IBM SP500. Are you following, guys?
Yes.
Okay, sorry, half. Perfect. Okay, so what we are going to do is we're going to, first of all, transform the data that is in, these are prices, levels. And what we want to do is we want to create differences, okay? Changes. So let's create, for example, for SP, that is SP500, let's create a variable that is going to be called DRSP, okay? This is going to be differentiated rate of SP, something like that. I don't know why I call DR, but let's see. So how do you create this data set? Take a look. Every time that you do something, it goes in here. So DRSP is simply D log, okay, of SP500. So what I'm doing, remember that there's two ways of creating returns, okay? One way is PT minus PT minus 1 over PT minus 1, so that's a simple return. And another way of computing returns, guys, is simply using the log difference, okay? So log difference indeed is, let me show you my screen. So let me move to the next one. So the common returns time t is simply going to be pt minus 1 over pt minus 1, correct? So this is the normal return that we always use. And the d log return, okay, so let's call it rt star, is simply log of pt over pt minus 1. Okay, now do you remember this is a natural log? If you apply the rule here, it's going to be, okay, so let's call it ln, much better. Ln of pt minus ln of pt minus 1. Okay? You see, and this is another way of defining returns if the frequency is very, very small. So we are going to use this one here. In eViews, guys, this operation here is called D-log. Okay, D-log of whatever. So it does this for you immediately. So if we go here into eViews, do you see my eViews now?
Not yet.
Nope.
No. Now?
Yep.
Yeah, perfect. So in order to create the D-log, guys, always when you want to create something, you go to the command window and you write generate, G-E-N-R, the generate. Okay, so space, and let's create a variable that is going to be called DRSP. So it's just the name. I don't know why I used the R. And then you simply type D-log of SP. Can you try that? If you click on that, you're gonna get this series here.
Professor, just a quick question. Are we supposed to be doing this in the file that you sent to us, the APT IBM SP GDP?
No. I sent you two files, guys. I jumped one process. You have the Excel file, yes, and then you have another Word file, the eViews file. Open directly the eViews file.
Yeah, we have the eViews file. When you open it directly, you have all of this pre-generated already.
Yes. But you know, I want you to test it. I just try it or name it differently, but just see that this works. Yeah, I know that you have this generated already. Really right. But just create one at least and check, just name this differently. You just can do this one and create this one here and compare with this data here. Can you do that? So create a new file and a new variable is going to be DRSP1, that is going to be D log of SP. And then I want you to compare with this one here using descriptive statistics. 1 minute to do that. Ready?
Yes.
And I told you, so I created this one here, and what I want you to test is simply to test these two, so I can create a group. And then I can see that, you know, they are exactly the same. And if I want to create descriptive statistics just to show that they are the same, just for practice, let's do individual, and they are exactly the same. And if you want to see the correlation, for example, guys. Oh, sorry, not this one. Where's my covariance analysis here? You can select the correlation. And then you click enter. Of course, you have 1, 1, 1. That just for fun. It's nothing. Make sense? Do you understand how to do that? Okay. Now, what happens with the CD is a rate already, but the rate, unfortunately, is written in an annual base. Okay. So here is what we have. This last one is you need to understand what I'm doing here. So what I'm doing here is the following. I'm doing 1 plus CD divided by 100 because the 5.67, for example, is not 500 times, it's 0.057, do you agree? So what I'm doing is I'm first dividing the rate. And this rate, guys, is an annual rate. So that's why I need to do 3 divided by 12. That is basically 1 divided by 4 minus 1. Okay, so I need to be sure that you understand this part here because we're going to be using this. Again, let me share. Imagine, guys, that you have an interest rate for 1 year equals 10%. Right? My question is, guys, what is the interest, knowing the 1 year data, what is the interest for 3 months? Okay, now these rates are always compounding rates. Okay, and as a compounding, this implies that I need to use the formula, the following formula. This is going to be equal to 1 plus I, 1 year, to the power of something, there is a ratio here, minus 1. So what goes up? The number of periods of what you try to find, and what goes down? The number of periods of the rate that you have. So you need to be careful. These are months and these are years. So we cannot mix units. So if I use 3 here, I need to use below 12. Do you agree with me, guys? That is the same if you simplify is 1 over 4. That's what we have in Excel. So if you want to find, for example, what is the interest rate for 1 month? So this should be 1.1, this part here, to the power 1 over 12 minus 1. So if you want to find the interest rate for 2 years, it's going to be 1.1, 2 divided by 1. You agree? Minus 1, etc. Questions? It's clear? So now let's go again to reviews. So this is what I'm doing here, guys. What I'm doing is generate CD1 equals 1 plus CD divided by 100 to the power of 1 over 4 minus 1. It is like Excel, you know, but in this case, we use the variable names and that's it. Make sense to you guys? Then you need to do the same for the, no, not the same. For the GDP, if you want the returns of GDP or changes in GDP, percentage change in GDP, you simply do D log of GDP. So you get your DR or DGDP. So you can see here, You see? You do the same with RBM, with IBM, it's D log of IBM, etc. So we have built all our series, guys, in differences, okay, returns. Now, what is the APT model? So APT model refers to arbitrage pricing theory. Okay. Do you remember that the CAPM model, guys, it simply says return of asset I minus the risk-free equals beta return of market minus the risk-free. Remember, this was the CAPM model. The APT uses this one here as one factor, but includes more factors, right? So what APT model says, for example, that the one I'm using, the very simple model is IBM minus the risk-free is CD. So this is IBM, returns of DR IBM minus DR, I think I call DR CD or DCD, I don't know. What's the name? Or C1, CD1, I don't know. Equals, now we have many factors. The beta one is going to be DRSP, representing the market, minus the, what's the name of the variable? Give me 1 second. I need to see what variable do we have. DRCD. Okay. Minus, so DRCD. So this is my market factor plus beta 2. And I have the economic factor. So DRGDP minus DRCD. Okay, so this is going to be, and then you can add more factors in industrial productivity, inflation, labor, etc. But the CAPM model, guys, sorry, the APT model simply says, you know what, the CAPM is a particular case of the APT model, because this one here is this one here. But you can add more factors, okay? Cyclical factors, trend factors, momentum factors, etc. Make sense to everyone? And so this is the model we're going to be working with, guys, okay? Remember, this is a deterministic model, but in econometrics, we don't have that. In econometrics, what we do is we have DRIBM minus DRCD equals alpha, or A, let's call it A plus B, B1 plus B2 plus an error. That's what we do. But it's a multiple OLA simply. And we are going to do that in eViews, and then we're going to analyze all the assumptions of the OS model. Okay, so let's go back to eViews. Now, guys, in eViews, what I will do is I will run my regression. So you go again, quick estimate equation. And when you go click estimate equation, this is the variable we're going to be using. Sorry, not this one. This one here. Okay, so DRIBM minus DRC. So this is risk premium of IBM should be equal to a constant, the risk premium of the market, and the risk premium of the economy. So this is the financial markets and or stock markets and the economy. Make sense? We have 162 observations, then we run this one here, and then we got these results.
Professor, would you mind going back to the estimate tab for just one more second?
Yes, perfect. Here we go. Yeah, 1 minute to copy this one. You get it?
Yes, thank you.
Perfect. So now if you run this one here, guys, please, I want you to give me very quickly. So which one do you prefer in this case? R squared or just R squared?
Well, there's 162 samples. So if there's any difference between the two, shouldn't you use adjusted?
Yeah, you know what, exactly. But you can see the difference is mild. Do you agree? And if this number goes up, these two numbers are going to be the same. Yes, but I agree with you. We prefer to use adjusted. Do we have the goodness of fit of the model? How is the goodness of fit of the model? Or what is a NOVA test, or what is a F test? What it tells you. So I'm talking about this part here, guys. What can you tell me about that?
There is a linear relationship.
Yes, because you are rejecting the null hypothesis of no linear relationship, so it implies that you cannot reject the linear relationship. Okay, good. Now, what about the alpha? Sorry, is the y-intercept statistically significant?
It is not.
It is not. At the 5%, this number here is much larger than 0.05, so you cannot reject the null hypothesis that this number is equal to 0. Can you test that using the Wald test that we have done a couple of minutes ago? Verify this conclusion using the Wald test. Verify that my restriction is going to be the coefficient number 1 equals 0. Do you still reject or not reject the null hypothesis? Guys, so you go view, coefficient diagnosis, Wald test, and remember, I want this one here, and I want this to be equal to 0. Correct? If you use, which one do you prefer here? Well, the sample size is decently large, so you kind of indifferent between the F and the chi-square. If it's small, you prefer the F. So what is your conclusion, guys? At the 5% significance level, do you believe that the coefficient for C equals 0?
Yes.
And how do you know that?
Because the probability is greater than the alpha.
Perfect. And that's it. Got it. Now, if you want to go back to your results, just go estimate, run this again, and then you have this one here. Now, guys, do you remember in the Kaplan model, IBM was believed to be the weight of IBM was supposed to be very close to 1, correct? because IBM normally moves with the market or moved with the market. Now, this last couple of months is crazy, but in general, IBM moves with the market. So the IBM is supposed to have a beta that is very close to 1. Can you test that? So the beta of the market is this one here. Is this one here, correct? This is the CAPM model. SP500 minus the risk-free. Okay, is this number, can I consider this variable here, the beta of this variable here, equal to 1? That is more or less what theory suggests.
Would we need to run another test, Professor? A different
Yes, yes, another Wald, right? We can do another Wald. How do I call this variable here? What I write in parentheses? See what? Guys, what is the position of this one here? Of the variable I'm interested?
C2, I suppose.
Yeah, C2. Remember, it's in order. So this is C1, C2, C3, etc. And I want to test if this one here is equal to 1. Right? Simply click OK. You tell me, guys. The null hypothesis is that I believe that this beta equals 1. What do you do? Reject or not reject?
Reject.
Reject. Okay, so it's clearly not equal to 1. It's significant, but it's not equal to 1. Significant because you can take a look to the coefficient. 0.028 is smaller than 0.05, so it is significant, statistically significant, but it is not equal to 1. Make sense? Now, if you want to see, guys, for example, you can start playing with actual fitted residuals. Let's do the graph, so you can see the fit. The fit in the last part is very nice compared to the fit here. It's very flat, and that's why in time we want to use more time series. But you can see all this part here. Now, guys, let's go to. Can you go back? Estimate here. So can I? Okay. So let me show you. So now we go into more serious econometrics. Okay, guys, you have seen that the OLS model is extremely simple to run in EViews. You can interpret everything. But again, we need to be sure that we are satisfied, and we're going to analyze model assumptions. Last class, we have done already one. So the first model is linearity. The first model assumption is linearity. Okay. So we have tested that, and we say that if we include the intercept, then sorry, no, it's not this one here. Simple linearity, we need to remember that the linearity implies linearity in the coefficients, in the parameters. Okay, so we said that we can use x squared, we can use the log function, etc. Right, so this is what we did last class. Also, last class, I think we said that this one here, this was my second assumption, should be equal to 0. And we said that this is true if and only if you include the y-intercept. Okay. And of course, you can eliminate the y-intercept once you determine that it's not statistically significant, correct? Like the case that we have in the EViews file. In the EViews file, the intercept is clearly not significant. So what we can do is we can simply remove it, okay? Can you run that regression? Can you run your regression without including the constant? Call your first regression. Call your regression. Oh, you have it already. It's called APT in the EViews file. This is called APT. Okay, you can close this one here. If you open APT no C, so no constant, what you need to do basically, guys, is the following. You simply run the risk premium of IBM, risk premium of the stock market, risk premium of the market, of the economy, without the C here. So that's the way it is not included with C. If you compare this one with a common APT, the normal APT, take a look to what happens. The coefficients are very, very close to each other, to these ones here. The R-squares don't change dramatically. But take a, where's my F here? Oh, I don't have to, that's okay. So the coefficients are very close to each other, guys. Okay, and unfortunately, when I delete my my y-intercept, so I am assuming 0, we disappear basically my F test here. Okay, we will explain this more, the probabilities on change, etc. Okay, perfect. So let's continue working on the assumptions. Now, guys, there is another assumption. The third assumption is more technical. It's very, very important. The third assumption, guys, is that the covariance of EI, EJ equals sigma square, okay, for all I equal J. Remember, guys, the covariance of EI is simply the variance of EI, and this variance of EI should be a constant. Okay, so this is the second assumption, that the variance of your errors should be constant. And this assumption is known as what? Someone remember? How do we call this assumption? Yes, homoskedasticity. Very, very long name. Homoskedasticity. Okay, so the OLS model, guys, requires the errors to have constant variance. Okay, the errors to be homoskedastic. Got it? What happens, guys? How do we see graphically, or just at least mentally, what is not a process that is heteroskedastic? So imagine I have an X here and I have an error here. One heteroskedastic possible behavior of the errors is something like that. You see, guys, this satisfies the first condition. The expected value of the errors is 0. You know, the up cancels with the down, so you are satisfying this condition. However, this is not homoskedastic because the variability of this data here is very small, and the variability of the errors around here it goes going up, 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 up. So this is not satisfying homoskedasticity. Got it? Unfortunately, guys, if we have a regression, we cannot see the graphs of X and E and just see all the X's versus E, or the products of X versus E, etc. So it gets more complicated. So that's why we need a special test, okay? And the test for heteroskedasticity is going to be the following. No, test for homoskedasticity. The first thing we need to do, guys, is run my regression. Okay, so this is my YT equals, I will call it beta 0 plus beta 1 x1t. Let's say that I only have two regressors, x2t plus my error. Okay, more or less what we have. This is IBM, this is the market, and this is the economy. Right? So first of all, you run this regression. And then what you do is you capture the errors and then you square the errors. Okay. So you run the regression, you capture the errors, and then you square the errors. And then what you try to see is what is the relationship of these square errors versus all the x's. So I will call this gamma 0 plus gamma 1 x1t plus gamma 2 x2t. So what I'm trying to do is I'm trying to see what is the relationship of the square of the errors versus the variables here. But also I can include the squares of these numbers here. So this is 3 gamma 4 x2t squared. And also I can do something that is called the cross terms. x1t that multiplies x2t plus an error bt. Okay, so this is another error. Make sense? So this one here is what is called a non-restricted regression. And this is the only one I will do. Later I will just refer to this type of things. Now, guys, do you understand that this one here by construction, as soon as we are talking about this one here, is square, so this should be positive number. Agree? Guys, are you there? I think I'm just talking to the computer.
Yeah, Professor.
We're here.
Okay, perfect. So first of all, guys, why is this one here important? Why I'm doing in the square of the errors? Because remember, guys, what is the variance of the errors equal to? The variance of the errors is simply the expected value of ET minus the mean of the errors squared. Agree? However, what is interesting is that we know that this one here is 0. So this one here indeed is simply the expected values of the errors squared. Right? So that's why we use the errors squared to analyze the variance. And that's what we're doing. We're analyzing the variance. We're trying to see if this variance is a constant. Right? Then what we do is we have a restricted equation that is simply this one here equals gamma 0. Got it? So basically, guys, our null hypothesis using the non-restricted equation is going to be that gamma 1 equals gamma 2 equals gamma 3 equals gamma 4 equals gamma 5, and all these should be equal to 0. So if this is true, guys, what is the hypothesis? Homoskedasticity or heteroskedasticity? What we are testing, homoskedasticity or heteroskedasticity?
Homoskedasticity?
Of course, errors are homoskedastic. Just take a look, guys. If gamma 1 is 0, this part disappears. What is left? Gamma 0. Gamma 0 is a constant. And this constant is my sigma squared. You see? So my hypothesis, guys, is going to be homoskedasticity. Okay, my test here is going to be the F test. And the F test is simply the sum of the squares of the residuals of the restricted minus the sum of the squares of the residuals of the non-restricted divided by its degrees of freedom divided by the sum of the squares of the residuals non-restricted. Okay, so if I have non-restricted, how many coefficients do I have? The degrees of freedom is n minus k. Do you agree, guys? Because I have 1, 2, 3, 4, 5, 6 variables. I lose 6 variables of degrees of freedom. So it's n minus k. When I have the unrestricted one, sorry, the restricted one, how many degrees of freedom do I have? Guys, I have only one coefficient here. It's n minus 1. For the restricted one, is n minus 1. Agree with me or not?
Yes.
And I need to subtract the degrees of freedom of the non-restricted that we said is n minus k. Okay, everything has a logic, guys. Why is n minus k? Because I'm having k variables in in my regression. Why is only one? Because I have only one variable in my regression. So if you simplify this one here, you get that this is SSR minus SS. Wait. So we use SSR or SSE? No, I think we use SSE for the errors. Because we need to be sure that this is the sum of a square of the errors, okay? Sum of a square errors. So basically sum of errors squared. Divided by, so if I do this, n goes out, so it should be k minus 1. Yeah, k minus 1. Divided by SS, this is SSE. SSE divided by n minus k. And this one here, guys, is going to be an f with degrees of freedom k minus 1, n minus k. Okay, if you realize, guys, this f k minus 1, also the people call it m, that is simply the number of restrictions. You agree? How many restrictions we impose here? 1, 2, 3, 4, 5. You agree? How many variables do we have, or parameters do we have? We have 6 minus 1. How many restrictions we have? 5. These ones, 1, 2, 3, 4, and 5. So this is m. Okay, so homoskedasticity is crucial, and I will explain you why. If you go to EViews, guys, we have everything done. So you know the process, what we are going to be doing, but EViews does this for you immediately. Okay, copy 1 minute, and then we go to EViews. We continue moving. Okay, so let's go to EViews. The first thing you need to remember, guys, is that you need to run the model. Okay, so let's use the APT with a constant. So run this again, just to be sure that you have the residuals. One thing with EViews, guys, is that these residuals here, this one here, represent the residuals of the RAS regression that you have run. Okay, so if you have many regressions, you need to be sure that, first of all, re-estimate the model. Now I'm sure that these residuals are the residuals of this model, right? Or if you want to play safe, you can say generate, let's call it residual 1 equal receipt. So in this case, what you're gonna have, this one here is not gonna change. This is a variable name. So you can use this one here, right? But in general, what I do is simply estimate again. I'm sure that the residuals are the correct ones, and then I proceed. Okay, how do we do this test here? You go coefficient test. Residual diagnosis. So you go view, residual diagnosis. View, residual diagnosis. And then you go here, you can see heteroskedasticity test. And then the name of the heteroskedasticity test that I just mentioned to you guys is called the white test. Okay, and here it tells you include the white cross terms. What is the cross terms? The one that was attached to gamma 5. Do you remember x1 times x2? The last term in our regression. Do you remember that? the one that we have just done. So I'm talking about this one here. So the cross terms, this is the one. This one here is my cross terms. I think they call it cross terms. Yes, cross terms. Make sense to you guys? Now, if we go to views, view, residual test, heteroskedasticity, white, include cross terms. Okay, here we go. What is the null hypothesis, guys? What is the null hypothesis? This is my cross term. This is the square of the first term, the square of the second term, levels of the first term, levels of the second term. So what is my null hypothesis here? What is the null hypothesis here, guys?
That it's homoskedastic.
Yes, so this implies that all these coefficients, except a constant, all these coefficients are going to be equal to 0, right? Because if all these coefficients are equal to 0, guys, the only thing that stays is a constant. You agree? And that's what we try to test. Is the variance of my errors a constant? Because that's what the model requires. If we don't have homoskedasticity, guys, we have some issues that I will explain in a minute. Make sense to you? So at the 5%, oh yeah, I need to tell you something more. So this is the F test, guys, but also we have the chi-square test, as usual. And the chi-square test, guys, is simply a chi-square with m degrees of freedom. What is m? Is simply k minus 1. So it's number of restrictions. Got it? It's the same as before. We always want to have an F test and we always going to have a chi-square test. Which one do you prefer when we have small samples? F test. If you have a large sample, you are indifferent, as the previous case. Okay, guys. So these observations times r squared. So indeed, you multiply the number of observations times the r squared, and this is this number. And then you simply go to the chi-square distribution and see if this number here falls in the critical value, to the right of critical value or left of critical value on this side. But you can use also the p-value of the test. Okay? With these two, this one and this one. If you base your decisions on the F, guys, you have M is 5 restrictions. This is n minus k. Okay. 3, 6. So we have 161 minus 6 is 155. So what can you tell me, guys, at the 5% significance level? Do this model, these errors, the errors from this model are homoskedastic or not?
They are.
They are. Why? Because your null hypothesis is homoskedasticity. Okay, and 5%, this 0.35 is larger than 0.05. So this implies that you're not able to reject the null hypothesis. You're not able to reject the null hypothesis that the errors are homoskedastic. So you don't have the issues with heteroskedasticity here. So you are okay with this assumption. Okay, so you are okay. So your model up to this point, your results are okay because you have errors that are homoskedastic. So this is a third assumption. Now, however, guys, I need to tell you what happens if you don't have heteroskedasticity, if you have heteroskedasticity. Everyone is with me here?
On the whiteboard, yes.
Yes, perfect. So let me tell you the following. Do you remember what is the standard deviation of the regression? So this is called standard deviation of regression. Regression, standard deviation. Okay. And this one here, simply, guys, is the sum of the errors squared divided by n minus k. Is to the power 1, square root of this. Got it? Now, what is interesting, guys, is the standard deviations or the standard errors. Standard errors, sorry, this is regression and standard errors, not the standard deviation. We're talking about the standard errors. The standard errors. What is interesting, guys, is that when we try to compute, for example, the standard error of alpha, of the constant, okay? This one here is simply sum of xi squared minus x, this one here. You need to remember this one here, divided by the square root of the regression, okay? Just to understand what's going on here. Now, if you have heteroskedasticity, then see what happens. If heteroskedasticity, imagine, guys, that in the equation, remember this equation here, EI squared equals gamma 0 plus gamma 1 x1t plus etc. Okay? So what happens if there is a positive relationship between the errors and some of the x's? So what is going to happen, guys? So this implies that if x grows, it starts increasing, what happens with the errors squared?
The error increases.
Also, do you agree? So if x is one of the x's or both or the multiplication or power increases, so this implies that this one here is going to increase. Now, if this one increases, what happens with the standard error of y? The standard error of the regression, this one here. If this part increases, all this part here increases. Do you agree? Guys, are you following?
Yes.
Yeah.
Okay, so this one increases. Now, what is the issue if this one increases on the standard error of the constant? So this is a constant, okay, what we call alpha. So what happens with this standard error of alpha? So this one here is increasing. The denominator is increasing. So what happens with all this ratio?
Decreases.
This ratio decreases. Okay? So when you have heteroskedasticity, guys, the parameters are still consistent, unbiased, sorry. Okay, so this is good. So your coefficients, your parameter estimates are not going to change. They're going to stay the same. However, guys, your hypothesis testing can be damaged by this type of relationships. So this implies, and this is stronger, guys, when you have problems. For example, this is my t, okay? Imagine this is my critical value, okay? My t critical value and minus t critical value. Imagine, guys, that you have the real t-test. Oh, sorry. Moving a little more. This is my standard error. Do you remember what was your t-test? Your t-test for this one here was a minus 0 divided by the standard error of this one here. Do you agree? So what happens when this one decreases? What happens with the t-test?
It decreases.
No, if this decreases, remember the denominator decreases.
Oh, then
so
it increases, right?
Exactly. This is going to increase. So imagine, guys, that your real t-test or your t-test is very close to this part here. Got it? If you have heteroskedasticity issues, guys, you can jump this one here into the rejection zone. Do you see? This is the main problem with heteroskedasticity. So heteroskedasticity, guys, affects the standard errors and affects the t-test and affects the test in general. They are still going to be unbiased, so the coefficients don't change. But the problem is with inferential statistics. My hypothesis testing, I can have some troubles there. I can have some problems there. Got it? So this is the main issue with heteroskedasticity. Please remember, parameters are still unbiased, but what happens is that standard errors are modified, and this can change your decision root, okay, incorrectly. Now, what solutions against heteroskedasticity, guys? When you find heteroskedasticity? Well, one easy solution that not necessarily works, at least for me never worked, but one solution is simply take logs of the data. Okay, the other solution, guys, is use the heteroskedasticity consistent standard errors. Heteroskedasticity consistent standard errors. This is what is called also white. Okay, so remember, guys, that the test, heteroskedasticity test, is called the white test, and the heteroskedasticity consistent standard errors is also called the white heteroskedasticity consistent standard errors, because this is the guy that created this test. In EViews, it's a piece of cake. If you copy this one here, we can move to the next slide. Ready? Okay. So let me go into EViews again. How do we do this? So let's estimate again, just to be sure that I have all what I want. Then what we have done is we have done a residual diagnosis. I have my heteroskedasticity test. I have my white test, include this one here. So this is my white test, okay? Now, I see that I don't have heteroskedasticity issues here, guys. That's the first thing I want you to know. Do you see that? I don't have issues here. So I should not do what I'm doing now, but I just will show you how to do it, okay? But remember, if I don't have the heteroskedasticity issue, I don't need to do anything. I just continue moving in the next assumption. Make sense? Please pay attention. Just because I want to show you, I will do it. You don't need to do it in this case, but I will do it. So let me copy this part here, just to show you what happens. And I will create another one. I will do quick estimate equation, and I will run this one here. And before running this one here, guys, the model is the same, the data is the same. What I will do is I will go to options. And then I do covariance method, HC, heteroskedasticity consistent. Yeah, that's okay. We don't need to do that. This one here, just click run. And I want to show you the following. Have you seen what I've done? Guys, have you seen what I've done? Yes?
Can you do it one more time?
Yes, of course. So what I've done is, okay, I estimated, this is my regression. Okay, everything is the same as this one here, as this one here. The only thing that I will do is I will use different standard errors. So you have this one here as ordinary. And here what we do is, oh, sorry, yeah, we have the white, Huber white. This is the one that I show you. Simply click Huber white and then simply click here, okay? And these are the results, right? What you need to understand, guys, remember I was telling to you guys, if you have heteroskedasticity, you don't have problem with the coefficients. They are still unbiased. Take a look to the coefficients. They are exactly the same. If you see these coefficients here, they are exactly the same as this one here. So this one is with adjusted standard errors, and this one here is with the simple coefficients. However, guys, what you can see when you make the adjustments, what changes? These values here. Before it was 1299, now it's 1556. Before it was 1576, now it's 1549. And of course, if the standard errors change, the t-statistics change, and the probabilities can also change. Make sense to everyone? So that's the issue with heteroskedasticity. Heteroskedasticity does not affect the coefficient estimates. The coefficient estimates are going to be unbiased, so this is good. However, the standard errors are going to be wrong, the t-statistics is going to be wrong, and the probabilities are going to be wrong. Makes sense to everyone? So that's why you need to analyze heteroskedasticity before moving forward. Questions?
So I have a question. You can still get reliable results even if you have heteroskedasticity, as long as you use the Huber-White.
Yes, of course, because exactly the
Okay.
Huber-White, what it does is simply change the standard errors. So your standard errors are going to be more robust to issues with heteroskedasticity. So they are whiter, basically. Right. So this one, if you don't have the problem with, if you have the problem with heteroskedasticity, you need to do this. Okay. If you don't have that, you don't do it. So you continue with your model as it is. So that's why I will delete this one. I don't care. Well, we can name it. So let's do HC. Guys, everyone understands, understand this part here, because this is a typical question of testing if you understand what we're doing.
Professor, just a quick question.
Yeah.
Nothing really confused about mathematics, but it's just to get there, you essentially click estimate again in the APT window and then click options, and then you switched it to Huber-White, and that's it.
That's right. That's it. That's it. Okay, that's what I'm telling you. Once you have this in EViews, everything is simple. It's almost everything is done. Exactly. But you get the idea, right?
But
so what you're doing is you are trying to adjust your standard errors in such a way that you capture this this heteroskedasticity present in your errors.
Yeah, but I do have a question though. How do you switch back? Because that only changes APT.
No. You can go switch back to ordinary.
Okay, cool. I just switch back to ordinary. I'm good.
And then that's it. And you're good. You're
okay.
Good. But remember, this is a process, okay, guys? What I'm trying to teach you here is just to be sure that your results are consistent, because you have beautiful results sometimes here, and the people start immediately analyzing the results, and that's wrong, because sometimes you have errors in the assumptions, or the assumptions are not satisfied. So thus you can have completely biased results, or you can have errors in the standard errors. Okay, you need to be careful analyzing what we're doing. Make sense to you? Yep, makes sense? Okay, so let me share my screen. Oh man, 7-9 already. Well, at least I will give you some intuition. The next assumption we're going to be working with, guys, is assumption number 4. It's basically the covariance of EI, EJ equals 0 for all I different from J. Remember? How do we call this assumption? How do we call this assumption? No autocorrelation. No autocovariance. That is the same as autocorrelation, no autocovariance. Okay, so this is my 4th assumption. What cannot happen is that there is a relationship between errors now with errors in the past. Right? So basically what we're going to try to avoid is situations that look like this. So for example, imagine this is E, t minus 1, and this is my ET. So for example, this one here, there is autocorrelation here, because if ET minus 1 goes up, the probability that ET is going to go up is higher. You see, there is a positive correlation here. Also, we can have negative correlations between ET minus 1, for example, and ET. So we can have something like that. So when ET minus 1 is negative or is going down, ET is going to go down also. And also we can have this type of behavior, guys. When it goes up, and then when it goes down, we break, and then we go down. and then we go up again. So this is another autocorrelated process. So what we expect, guys, what we really hope to have is something random. It's something like that. You see, there is no clear pattern between ET minus 1 with ET. So this one here is non-correlated, non-autocorrelated. This is positive autocorrelated. And this is negative autocovariance. And this one here is also positive, okay? So what we try to do is this one here. Now, I think we need to stop here because the next step. So guys, we are very close to finishing this part here. So I believe that we finish this. So let me save this one here. So let's do some timing here. We're gonna finish this on the 6th of April already. That's amazing. And the second quiz is going to be on the 13th. Okay. On the 6th, I will finish half class. I imagine I will start time series, and then I will do this very quickly. This is good. For time series, guys, I will do the same. Do you remember for the introduction of OLS model, I did a lot by myself. I wrote all the math, and you need to review the math. I will do the same for the introduction of time series because it takes at least half of a class of very simple math, but very long math. So I will do that online. I will post this online for you. You need to study, and then we move from there. Okay, guys. I need to jump in my other class. Next time, see you. Yeah, go ahead.
Will time series be on the next quiz or just this stuff?
No. Just OLS, pure OLS. You know, guys, what is crucial about the OLS model is the benchmark model. You know, it is that the model that you are going to be using all the time for testing and seeing if the things more or less make sense, etc. But for that, you need to be sure that what you are doing is correct. And that's what we're doing here. And then we go time series is going to be, the first time series is going to be ARIMA models, Gauge models. This is the third test. And the last test is going to be multivariate time series models, VAR, Beck, and multivariate Gauge. So that's the fourth test. And then that's it. And then we have the oral exam, that is the final exam. Make sense? Okay, guys, please study. This part here is very dense. No, it's not dense, but you understand it's very logic. And if you get this part here, the time series part is going to be much simpler. You're going to get what I'm talking about when I talk about these common things. Got it? So study, we have just have in mind that we have the second test on a couple of weeks. Okay, guys?
You said the quiz is on the 13th, right?
13th, yes.
Okay,
13th.
Thank you.
Okay, perfect. See you guys. Take care.
Thanks, Professor.
See you. Bye-bye.